Hello again. Picking up where we left off, we were looking at this notebook easy equation NN5 in Colab, and it contained what? It contained a hello world, a single neuron trained to do a simple task in a Python notebook. And we got as far as creating the neural network in a object and compiling it. So we now have an architecture. We have, the methods that's going to be used for training it. So let's try training it. First, we'll need some data. So the good news is that this is really simple data. Y equals 2x plus 1, right? So we make two parallel arrays. The first one contains the x values, and the other one contains the y values. This is really typical of training neural networks. So the x values here are single numbers, but if the x values were, images, then this would be a list of, three-dimensional arrays, where each three-dimensional array was an image, right? And then the y values would be maybe something similar to this, where you would have, a number for each different type of object you're trying to notice, okay? For categories. So, but anyway, this is really simple. Minus 1 times 2 plus 1 is minus 1. 0 times 2 plus 1 is 1, all the way up to 4 times 2 plus 1 is 9, okay? So we have here what? We have half a dozen training values that range from minus 1 to plus 4. All right. If you haven't seen it before, these are called NumPy arrays. NumPy is a module of subroutines that you can call out of Python, which do numerical operations much more efficiently than using the Python lists. So that's really all they're for. So here is the setting up our data. So this is just our data for training the neural network. X values and Y values, two arrays. That's it. That's all we needed. Okay. And we can print them out and see them in notebooks. Now we're going to train it. This is to train it. That's this method called fit on the object. We give it the x values, the y values, and we say epochs equals 1. Epochs is counting the number of times you go through the entire data set. One epoch goes through the whole set of data. And you're going to have to go through the data set typically many times before the values are all nudged into place. But just to get started, we can do this, and what is its complaint? Says I hadn't compiled it. One moment. Yep, I forgot to compile it. Let's compile it. There we are. And now let's try doing this again. Okay. So it ran once, and it's telling us at the end of each epoch, of which we had only one, what was here. It says loss. That's the value of our error. So the mean squared error here was almost 18. So adding up the errors from each of those 6 test cases, adding up the squares and dividing, we got an average error here of about 18. When I did this in class, the smallest that anybody reported after one training epoch was 13, and the biggest was 69 or 68, something like that. Why are they so different? They're so different because the neural network starts with random numbers. So every time you create this neural network and start training it fresh, you're starting with random numbers for the weights. So, all right. Anyway, this seems pretty bad, right? We agree that's 17. And in particular, we could try some test data. We can put in 1.5. 2x plus 1 is going to be what? 4. Actually, we got about 1.05 out. So this thing is not trained. Over here, we'll do this again for 49 epochs. And that happened really fast, but let me show you what came out. Remember, after one epoch, the error was 17 or 18. This is now 1 of 49, meaning it's actually number 2 because we already did one earlier. And now it's 14. After the next epoch, the error is now 11. And now it goes down to 8.5. And we see the error slowly getting better. So that by the time we're done with the 49th epoch here, the 50th in total, because it's an object, it's keeping all these trained weights inside of this object. Okay, our error is now about 0.04, 0.05. So this should be better. So if we run this, we get, well, so minus 2 times 2 plus 1 should be minus 3. That's minus 3-ish, kind of off. 1.5 times 2 should be 4. But, when we include the plus 1, it's 4-ish. 6 should be 13. So we're getting in range, but we're still off by a good amount, okay? So how can we fix that? Well, just train it some more, really. Here we're going to train it for 300 more epochs. All right, you'll notice that training it for 300 more epochs, remember our loss error there at the end of the 4950 was about minus 0.04. We start out with minus 0.04. That object contains the neural network trained that far. And then after another 300 epochs, our error is what? It's down in the 10 to the minus 4th range. 8 times 10 to the minus 5. We're probably never going to get to exact perfect training. These are floating point numbers. They have, 15 or so significant figures. And we're training, multiplying numbers that have, 15 things after the decimal point by little fractions, nudging them. But, getting an error of 10 to the minus 4 is getting close, and we probably cannot actually train it to be exactly right. But we can give it some more test values, and what comes out? Minus 5 times 2 plus 1 should be minus 9. Here we have minus 9.03. Minus 2 times 2 plus 1 should be minus 3. All right, we're a lot better now. We're 1.5 should be 4. We have 3.99 something. All right, 10 times 2 plus 1 should be 21. We have 21.0 a little bit. So this is pretty good. I want you to notice something else, which is what makes neural networks useful. You'll notice our training data went from minus 1 to plus 4 or plus 6, something like that. Our testing data here goes from minus 5 all the way up to plus 10. And this is deliberate, and this is one of the reasons that neural networks are so successful. Because of that linear model, because we didn't code a bunch of simple if statements, if this, then that, if this, then the other, okay, it's entirely possible with the if statements the input could be out of range of the things that we considered. With the linear model, no input is truly out of range. I mean, it might be beyond what we trained in. It might be in a range where it's not going to do very well. But it won't just break. And in this case, it's actually doing pretty well with data which was outside of the input range. And now we've done what? Well, from a certain point of view, all we've done is we've now written a piece of code that computes y equals 2x plus 1. That sounds like a CS1 assignment, right? But what we actually did was we created a piece of code which learned from data. It looked at some data and it changed itself to compute that value. We didn't write a piece of code that said y equals 2x plus 1. We wrote a piece of code that looked at some data and learned to compute y equals 2x plus 1, just from examples. And it works outside of the range of data. So that was our kind of hello world moment, where we've seen hello world come out from a single neural network. And with that, we will save this.